Designing and optimizing different mechanical systems requires various tests and trials, which are usually very costly and time-consuming. For this reason, the design and construction process faces many challenges. The answer is computational fluid dynamics. Computational fluid dynamics is, in short, a method for simulating and analyzing fluid problems in engineering. In a more scientific language, this is about a process in which a physical phenomenon that involving fluid flow is mathematically modeled and solved by numerical methods. Many of these phenomena include fluid flow, fluid forces, heat transfer, and others that fall into the realm of mechanics, and especially fluid dynamics. The main goal of fluid mechanical engineers is to study fluids and predict their behavior. In this study, among the methods for solving fluid equations, we deal with the numerical solution method of equations. In the numerical solution method, differential equations are converted to algebraic equations, and by dividing the solution domain into smaller cells, elements, and applying boundary conditions on them, a system of linear equations is created, and by solving this system for all elements and with many iterations, which is the basis of numerical calculation methods, finally we come to an approximate answer with appropriate accuracy. In fact, in this method we convert complex geometries into a large number of simple and small geometries and solve equations over and over again for small elements. At this time, if you are thinking about what exactly iteration is, and what it means, I can tell you iteration is the act of repeating a process with the aim of approaching a desired goal, target or result. Now the question may arise for you, what is the intended purpose? It is the accuracy that the researcher has defined based on the number of decimal places. Because the target must be a kind of stop criterion, CFD software provides a stop criterion that is calculated either through a default stop condition after several iterations or by the user specifying the stop criteria in a special condition. As you can see in this slide, there are two ways to reduce the error in the numerical method. The first method is to increase the number of elements, and second by increasing the polynomial order in the elements, using more nodes. As you know, increasing the number of elements in a modeling has a computational cost and will not always be the best approach. Many factors must be considered in meshing a model in software. For this reason, instead of increasing the number of meshes in the whole area, we reduce the size of the element in the area of interest. That is, in the part that has the most stresses and differences. This is accessible through ANSYS Fluent capabilities in meshing. We will discuss this in more detail in the following videos. Now let's talk about numerical methods in fluid mechanics. There are three main methods: finite difference method, finite element method, and finite volume method. Using the finite difference method, a continuous environment can be converted to a discrete environment and rewritten equations and calculated partial derivatives in it. The basis of this method is the complete elimination of differential equations or their simplification to ordinary differential equations and solving them by numerical methods. For example, COMSOL multiphysics engineering software use this method to solve equations. Finite volume method, FVM. The finite volume method is a finite element method in which general conservation equations, conservation of mass, conservation of momentum, and conservation of energy, are used in integral form. The solution range is divided by a certain number of adjacent control volumes and the equations are solved in that range. The quantities are calculated at the center of the nodes and intermediation must be performed to obtain values on the surfaces. The finite volume method is applicable to all geometries, including complex geometries. This method is more suitable for solving computational fluid dynamics and heat transfer problems. For example, Fluent software uses this method. To better understand the numerical method, let's consider an example. A simple example of two-dimensional constant heat transfer in a plate. Now divide the xy plane of the region into a rectangular mesh of nodal points spaced dx and dy apart in the x and y directions, respectively, and consider a general interior node as shown in figure. In this example, for simplicity, we will consider only four elements. The energy balance on a surface element interval can be expressed as below. Heat transferred into the surface from all of its sides plus heat generated within the surface is equal to the change in the energy content of the surface element. The second and third semesters of this relationship are zero due to zero heat generation, and steady conditions in this example, so they are consequently eliminated. Noting that the surface element centered about the general interior node involves heat conduction from four sides, The steady finite difference formulation for a general interior node can be expressed as below. From the conduction heat transfer equation, this relation can be rewritten as follows. In finite difference analysis, usually a square mesh is used for simplicity and thus dx and dy are taken to be the same. Then dx equals dy equals 1, and the relation above simplifies too. Thus the finite difference formula of an internal node is obtained. Thank you for watching. Subscribe us to watch the step-by-step tutorial videos of ANSYS Fluent in next videos. And if the content was useful, please like it.